Welcome to lesson 15, related rates. So we know that derivatives are instantaneous rates of change. And usually when we have been taking derivatives, we've been taking derivatives with respect to x, dy dx. So it's kind of measuring how the output, the y, is changing with the input, the x. But what we're going to do in related rates problems is we're going to look at how various quantities are changing over time. So specifically when those quantities are related to each other. So let me give you an example. You have air that's being pumped into a spherical balloon. And so both the radius of the balloon, right, is changing over time, as is the volume of the air in the balloon. So that's a situation where you have two quantities, radius and volume, and they're both changing over time as the balloon is being pumped up. So I want you to take a second to answer this question. If the volume is increasing at a constant rate, like you turn on a pump, right? So it's just flowing that air in at a constant rate. Do you think the radius is also increasing at a constant rate? Why or why not? So take a minute to think about that. Maybe pause the video. So the answer to the question is no. The radius will not increase at a constant rate. And the reason is because when the balloon is quite small, the radius will increase very quickly. Like it will double. If it started at an inch, it will very quickly become a 2-inch radius, a 3-inch radius. But once the balloon, I mean, we don't have an overall capacity of this balloon, but let's say it was pretty big. And so by the time you get to a 15 or 16-inch radius or something like that, it's going to take a lot more air to increase that radius to 16 inches or 17 inches, right? So if you're pumping the air in at a constant rate, the more air you have, the more slowly your radius will increase. Another very classic related rate scenario is a ladder leaning against a wall, and maybe then the bottom of the ladder starts to slide along the ground, right, away from the wall. So that's going to make other things change that are related to that. Other geometric things change. So if we actually go to the next page, there's a picture here. Here's my ladder, here's my wall. And if this base starts sliding this way, we can see a couple things. The top of this ladder is going to come down, right? So this side of this triangle, H, is going to decrease. What about this side of this triangle? As this goes this way, the X will increase, right? It'll get bigger. And so that helps us answer the questions here. Would you expect dx dt, so the change in this side with time, would that be positive or negative? Is X getting bigger or smaller? X is getting bigger. So this would be positive because X is increasing. So its change over time would be a positive number. It's getting bigger. But the flip side of that is that dH dt is negative. And that is because H is getting smaller. So we do have to pay attention in these problems. We will often be given a rate, but the problem might say, oh, it's getting increasing or decreasing at the rate of 3 meters per minute. But if it says decreasing, then we need to use a negative number for that rate. So there is a bit of interpretation that you need to do. Okay. So we're going to kind of walk through this classic air being pumped into the balloon problem. And then once we do that, we will kind of go through the pattern of steps that you can use to try to solve a related rates problem. Okay, so here we are. We have air being pumped into a spherical balloon at a rate of 4.5 cubic feet per minute. Okay, so right here, we are given a rate. It is a rate of change. It is a rate of change based on time. So what is it that we're measuring here? If the air is being pumped in at a rate of 4.5 cubic feet, that's a big hint, per minute. That is a dV dt. It's the change in the volume because it's in cubic feet per minute. And since the air is being pumped in, we know that this is a positive amount. So I'm going to write myself a little list of things that I know, and then I'm going to write myself a note about the thing that I'm looking for. What do I want? That helps you organize your information in these problems. So I know that dV dt is 4.5. And the question is asking me, how fast is the radius changing? So that seems to me that I want a dr dt. And then it's giving me a snapshot moment when the balloon has a radius of 2 feet. So what's really important to notice in this type of problem is that when the balloon has a radius of 2 feet is that instantaneous moment that they're asking about. It is not true that the radius is 2 feet this whole time. It is not a constant, right? Air is being pumped in, balloon's getting bigger, radius is constantly changing. But when we talk about instantaneous rates, we need to have that moment at which we're measuring that rate. Okay. So the way we denote that in this want scenario is we draw a vertical line and we'll write R equals 2. And that is a way of denoting that this is what we're looking for at this moment. So this is what I know and this is what I want. Once you have this written down, the best thing to do is come up with an equation that relates the thing you know, volume, or the thing you know about, volume, with the thing you want to know more about, radius. So I will generally give you sort of obscure geometric formulas that you haven't used in a very long time. But the volume of a sphere is given by volume equals 4/3 pi r cubed. So here we have volume and radius related to each other, and there's no other variables in the way. So we're ready to go ahead and differentiate both sides with respect to time, or t. Okay. So that will give me dV dt equals 4/3 pi times 3r squared dr dt. So it's an implicit differentiation. And every time you take the derivative of any variable, since you're differentiating with respect to time, it has to be multiplied by the d whatever dt. Okay. So the derivative of volume v is just 1, but then I multiply it by the dv dt. The derivative of the r cubed is 3r squared times the dr dt. And it is at this point where, after a little cleanup, we can now substitute in the things we know. We know that dV dt is 4.5, and in this moment, the R is 2. I did not want to put the R is 2 in here because that would indicate that the volume was constantly using an R equals 2, which is not true. So 4.5 here, 4 pi times 2 squared times dr dt. And then it's just kind of a matter of dividing over the 4.5 by the 16 pi, which is the same as 9 over 32 pi. And I should add some units. So what would we expect units to be? R would be a linear, so not a cubic feet, but just a feet. And T is in minutes. So this would be, whoops, this would be in feet per minute. And we could get a decimal approximation to have a sense of about how much that is. But in general, most of the derivative, some of the derivative depends, asks you for exact numbers. Okay. So I'm going to let you go ahead and answer these questions about intuitively. So just want you to kind of touch base with your own knowledge of this situation. Like, why does the rate of change of the volume affect the rate of change of the radius? And why does the current radius affect the rate of change of the radius? But what we're going to do here is go on to guidelines. So how do I approach a related rates problem? Okay. So first of all, you're going to need to read the problem multiple times. I can't stress enough that you are not supposed to read it and just go, oh, I know what I'm doing. These are complicated problems, and they take time to sort through the information that you're given. That's normal, okay? So then you're going to want to draw and label a diagram, if possible, right? That illustrates what's going on. You might have to come up with some variables, right? You should do all of that methodically so that you have a good idea of what the scenario even is. Then I would suggest you do your know and your want. So you're going to then identify quantities that you know. And what you need to find. And I would write them down. It makes a difference. So then we need to either find or create an equation that relates the knowns and unknowns. Oftentimes, this will just be an existing geometric formula, like the volume of the sphere, right? Or the volume of a cone, or the Pythagorean theorem, or something like that. Okay. Then you will need to differentiate both sides with respect to time. And then lastly, you're going to sub in the known quantities and the moment values. So they're not necessarily constant the whole problem, but at this moment, right? And then solve for the unknown. There's one little thing I wanted to add here, and it's right here. When you find or create an equation that relates the knowns and unknowns, you may need to eliminate extra variables. And when we do that, in many cases, it's using similar triangles. And so we are going to look at an example of doing that. But if you have, let's say we were doing something that had a volume and it had both a radius and a height, but you didn't know anything about the height, you only knew about the radius, you're going to have to eliminate that height from your equation before you take a derivative. Otherwise, you're going to have a dH/dt that you can't fill in, and you'll have too many unknowns. So we will get to an example of that in the next video. So one thing I want you to do is, or two things, I guess, I want you to do is avoid these things. very common mistakes that are made. So the first one is plugging in the variables too soon, or the values too soon. Do not plug in the moment values before differentiating. Those come in at the very end because it's talking about a derivative at this moment. So you have to get the derivative first before you can plug in. This is now the R is 2. If you plug it in before that, it's basically like claiming that the R is always 2, which it's not. Okay. And then last but not least, you want to be sure to pay attention to signs. For given rates. And so, in other words, a rate is positive if that value is increasing, it's getting bigger. But a rate is negative if that value is decreasing, it's getting smaller. But it is not going to be given to you as a negative. It's just going to say that this is getting smaller at the rate or decreasing at the rate, or even just it'll be clear from the scenario that you draw, oh, that's getting smaller. And so it'll be up to you to use the negative. And I often get students go, oh, well, I had it right, I just didn't make it negative. But there's a huge difference between something increasing at a rate of 3 feet per second and decreasing at a rate of 3 feet per second. So it's not even, I was so close. You were actually off by 6 feet per second, which is a lot, right? So make sure you're paying attention to when you first write down your values of your known rates. Are they positive? Are they increasing or decreasing? So should that rate be positive or negative?